Alright, so today we're going over free fall in physics. So there's going to be some essential equations to note from here and variables. So first is going to be the free fall equation, which is going to be time is equal to square root of 2 over g, which is gravity, which is 9.8 meters per second squared, and then times square root of h, which would be the height of the free fall. And now free fall acceleration is negative g, which is negative 9.8 meters per second squared, which just basically denotes the rather shows the direction of the free fall, which is always going to be downwards because it's gravity. And now we also have the final velocity equation. So this is definitely something important to note. You can also deduct initial velocity through this and whatnot. And then these are just some simpler deductions, which would be delta v, how to find delta velocity, how to find acceleration, and then how to find displacement, which would just be velocity times delta t. Alright, so let's move on to number 20. So for these, you could pause the video and do them by yourself, which is why I also wrote the equations that are going to be necessary right here. So you could pause the video and try it out, but let's get started with this. So ball bearings are made out of letting spherical drops of molten metal fall inside of a tall tower called a shot tower and solidify as they fall. If a bearing needs 4 seconds to solidify enough for the impact, how high must the tower be? So we're given the time here and we need to figure out the height of the tower. And when we're speaking with height, this equation comes to mind. We're given the time, we know the free fall acceleration, we don't know that height here. So let's start plugging in stuff. So for t, we have 4 seconds. And then inside the square root, we have 2 over 9.8. And then we have square root of h. H is something we don't know, but now we solve for it. So the square root of 2 over 9.8 is going to be 0.452, and then times square root of h. And now we just divide by 0.452 on both sides. And we get that radical h is going to be equal to 8.8495, or you could just write it as 8.85. And now to find h, we're going to have to square root that, which is going to be 78. H is equal to 78.32 meters. And that is going to be our height for the tower. And now we need to find B, which is going to be, what is the bearing's impact velocity? So for the impact velocity, that's telling us that we need to find the final velocity. The equation for final velocity is going to be this one right here. Because this one's the best one to use because we know the initial velocity because free fall always starts at 0 meters per second. And then we know the free fall acceleration, and then we just figured out delta S right here. Delta S, which would be our height. So it would be V2 final is equal to V initial squared, which is going to be just 0 squared, plus 2 times 9.8, which is going to be our free fall acceleration, but it's going to be negative 9.8 because it's in the opposite direction, or downward direction. And then delta S is going to be 78.32 meters. And if we solve for that, we're going to have V squared final is equal to 39.141. And the square root of that, or rather actually, it's going to be 1,535. And then velocity final, you would square root both sides. That would be 39.141 and meters per second. Now that is the longer way to do it here, but I rather want to put this equation into application here. Another way to figure it out, the final impact velocity, is that we're given the time, and since it's free fall, we know that free fall acceleration is 9.8 meters per second squared. And since we're given the time, we could just figure out the final velocity. It would just be 9.8 times 4, which would give you 39.2. meters per second, or negative 39.2 meters per second. And we can see that that's really close to what we got, 39.141. Obviously, we did some rounding, but that would essentially be a faster way to figure out the answer. But knowing how to use the equation is also very important. All right, so let's take a look at number 21. So number 21 is a rock is tossed straight up from the ground level with the speed of 20 meters per second. And when it returns, it falls into a 10-meter deep hole. So we're going to break this question up into two little questions here. So let's first calculate the time in which the rock rather, is thrown straight up from 20 meters per second. Let's calculate the time it takes for it to stop, for it to reach 20 meters per second and then peak. So to do that, we would use the first equation right here, velocity final equation, in which our velocity final, we know that that's zero because we want to find out in the point in which it changes direction. So we have 0 squared velocity initial is going to be our 20, which is 20 squared, and then plus 2 negative 9.8 squared, or negative 9.8. And then delta S is what we don't know. We want to figure out the distance in which it goes up. Because if we find the distance at which it peaks, we can figure out the distance, or rather the time that it travels downward, and the speed as it hits the bottom of the hole. So if we solve for S, we're going to have negative 400 is equal to negative 19.6 delta S. And now 400 divided by 19.6, we have two negatives on both sides, so those are positive. That's going to give us delta S is equal to 20.41 meters. Now let's draw a little illustration. Let's say the person is right here, and this is the rock. It's going to be this blue dot here. And let's say the 10-meter deep hole is down here, 10 meters, and he throws it straight up. 20 meters per second initial velocity. So this is what's going to look like. We just found out delta S from when he throws it is 20 meters. So the projectile of the rock is going to peak at 20 meters right here. 20.41 meters. So we know the top most point of the rock and the bottom most point is going to be 20 plus 10, which is going to be, or 20 minus negative 10, which is going to be 30.41 meters. So delta S of everything is going to be equal to 30.41 meters. And now we start answering the questions. Now we know that stuff. So what is the rock's speed as it hits the bottom of the hole? So to do that, we're going to use the first equation right here, in which we know the initial velocity is going to be 0, because when it gets to this peak point right here, up here, the rock is now in free fall. It's going to go straight down, in which it's going to start a velocity of 0, because when it peaks, the velocity is a tangent line on a graph in which it's 0. So we're going to have v final squared is what we don't know. We want to figure that out. And then v initial is going to be 0 squared plus 2 negative 9.8. And then now we know delta S, which is going to be 30.41. That's the distance it falls into the hole. So now we want to solve for v final, in which it's going to be 30.41 times 9.8 times 2. And we're going to get v final squared is going to be equal to 596. And now we just square root both sides, in which we're going to get v final is equal to 24.4 meters per second. And that is going to be the rock speed as it hits the bottom of the hole. And now we want to figure out how long is the rock in the air from the instant it is released until it hits the bottom of the hole. So what we're going to do is we're going to keep that broken equation right here. So In order to find the time of everything, first we're going to find the time of when he threw it to when it peaked. So in order to do that, since that's not free fall, we can't use the free fall equation. So we can use the equation acceleration is equal to delta v over delta t. Because we know acceleration and we know delta v. Delta v is going to be the initial velocity minus the final velocity, or rather final minus initial. So if we plug that in, we know acceleration is going to be gravity, which is going to be negative 9.8, is equal to 0 minus 20, which is change in velocity, so negative 20, and then delta t is what we don't know. And if we solve for t, we're going to get 2.04 seconds. So 2.04 seconds in this little diagram is going to be how long the ball was going up in the air. Now we need to find out the time for it took to fall. So to do that, we just use this free fall equation. So we're going to have time is equal to square root of 2 over 9.8, which is going to be our free fall, times square root of h, which is going to be our height, which is 30.41. And if we do the calculations, we're going to get t equals 0.4517 times square root of 30.41, which is going to be 5.515. And then if we multiply that, t is going to be, our final t value will be 2.49 seconds. So we just found the two time intervals in which we broke up this diagram or equation into. So now if we add together the two time intervals, we're going to get the total time, in which it's going to be, t is going to be equal to 4.53 seconds. And that is how long the rock is in the air for the whole time it is released until it hits the bottom of the hole. Alright, so let's move on to number 23. So as a science project, you drop a watermelon off the top of the Empire State Building, 320 meters above a sidewalk. It so happens that Superman flies at the instant you release the watermelon. Superman is headed down straight with the 35 meters per second velocity. How fast the watermelon go when it passes Superman? So let's draw a little illustration here just for visualization. So let's say you're right here on the Empire State Building. You drop a watermelon, which is going to be right here. So this distance to the sidewalk, which is right here, is going to be 320 meters. And this ball is going to be in free fall. And now we have Superman, which is going to be, I'll draw him like upside down. And he's moving at 35 meters per second in a uniform motion. So he's moving at constant velocity. So how can we figure out how fast the watermelon is going when it passes Superman? Now, there's some things to know here. So when the watermelon passes Superman, their positions are going to be the same. So delta S is going to be the same. How can we kind of set two equations equal to each other in order to find the time in which they pass each other? The watermelon passes Superman. So if you remember, delta S is going to be equal to velocity times time, delta t, and then delta S is equal to half gravity times t squared, in which this is not a new equation. This is the same thing this is the same free fall equation we looked at, in which it's just a different iteration of it. So we can actually solve for it just so you guys can see how it's the same. So this is the free fall equation, t equals square root of 2 over g times square root of h. Let's say we square both sides, or if we square everything. If we square everything, we're going to have t squared is equal to 2 over g times h. And h is going to be s, by the way. They're the same thing. H is going to be delta s. So we want to solve for h here. So if we solve for h, we're going to multiply by g on both sides. And then so we're going to have gt squared is equal to 2h. And if we divide by 2 on both sides, we're going to have h, or delta s, is equal to 1/2 gt squared. So you could kind of see how it's the same exact equation, except I just rewrote it out. So what we could do now is set both of these equations equal to each other because, so for Superman, we know that his velocity is constant and we don't know time. So since position for both of these have to be equal, we can just set these equations equal to each other. So we're going to have velocity delta t. This is going to be Superman's equation. We could just label the equations. And then that's going to be equal to the watermelon equation. The watermelon is going to be denoted by the free fall because the watermelon's in free fall. We're basically giving both of the particles here equations. So the watermelon's equation is going to be 1 half g p squared. And we can remove this delta. It's a little unnecessary here, but now let's start plugging in stuff and solving. So Vs, what's Vs, the velocity of Superman? We know that's 35 meters per second. And this is all going to be in the downward direction, so that's why gravity is going to be positive because Superman's downward velocity is also positive here. So 35 meters per second is Vs. T, we do not know that yet. And then we have half times g, which is going to be 9.8. We know that. And then t squared, we do not know that. So now we have a t squared and t on both sides. What can we do to leave us without only one t? We can divide by t on both sides. If we divide by t on both sides, that kind of get rid of some problems here. So we'll have 35 on the right side, and then 1 half times 9.8 is going to be 4.9, and t squared divided by t is just going to be t. 35 is equal to 4.9t, in which if we divide them, so if we divide both sides by 4.9, we're going to get that t is going to be equal to 7.14 3 seconds. So the watermelon passes Superman at 7.143 seconds, but we're trying to find how fast the watermelon is going when it passes Superman. So we know that the it passes Superman after 7.143 seconds. What we could do is just multiply it by gravity, the acceleration of gravity, because it's in free fall. So if we multiply this 7.143 by 9.8 meters per second squared, we're going to get a velocity of exactly 70 meters per second. So when the watermelon passes Superman, the watermelon is traveling 70 meters per second downward. And that is going to be our answer. Alright, so let's start number 25. So number 25 is a rock is dropped from the top of a tall building. The rock's displacement in the last second before it hits the ground is 45% of the entire distance it falls. How tall is the building? So we're going to use the free fall equation here. This is again the iteration of the original free fall equation I just solved for h. Now we know that the rock covers its 45% of its fall distance in 1 second or the last second. Now that's not gonna, we can't use 45% as because we don't know the final velocity of the rock, but what we do know is the initial velocity, which is 0 because it's in free fall. So we can find the rock's first 55% of the entire fall, and then we can figure out the height of the building through that. So first, let's solve for h here and plug in the necessary variables. So h is equal to half, g is going to be 9.8, so half times 9.8 is going to be 4.9 t squared. Now we're going to leave that like that. Now how can we turn h equals 4.9 t squared into something that covers the first 55%? Because 100% minus 55% is going to be, or 45% is going to be 55%, rather. So in order to do that, what we could do is on the left side is going to be 55.55 times h, because it's going to be the first 55% of the height times 4.9. And inside the parentheses, we're going to have t minus 1 because we want to find all the time that it falls except the last second. So the last second, in order to eliminate that, we're going to add that minus 1. And then that's going to be squared. And we also don't want two variables in here because we want to solve for t. How can we replace h? We have this original equation here, so we can just replace h with 4.9 t squared. So if we rewrite it out, it's going to be 0.55 4.9 t squared is equal to 4.9 t minus 1 squared. And now we're going to start multiplying stuff out. Let's write it out up here. So the left side is going to be 2.695 t squared. And then the right side is going to be, first we're going to factor out, or rather multiply out the t minus 1 squared, which is going to be t squared minus 2t plus 1. And now we're going to want to multiply out the 4.9, so it's going to be 2.695 t squared is equal to 4.9 t squared minus 9.8 t, and that's going to be plus 4.9. And now all we need to do is just solve for t. So to do that, what we're going to do is we're going to get everything to one side right now. So we're going to have 2.205 t squared minus 9.8 t plus 4.9. And now this is the quadratic function that we have. So we want to factor it out and solve for t because t is essentially going to give us our time. And then through that we can find the so how tall the building is. So if we factor out t, so we can't exactly do it the conventional way, but we can use the quadratic formula. Now I'm gonna cut a lot of time here and just give you guys the answer for t. So it's gonna be, and we're gonna get that t is equal to 3.87 seconds, in which now, and so with this t equals, we know that the rock takes 3.87 seconds to fall down the whole tower, or building rather. So all we need to do is just plug it into our original freefall equation, and then we'll get h. So h is going to be equal to 1/2, 9.8 times 3.87 squared. And if we calculate that out, we're going to get that h is equal to 73.4 meters. Or rather, h is equal to 73 meters. And that is the height of the building. Alright, so that was basically it for freefall. So freefall, these two equations right here, the original freefall equation and the velocity final equation, are definitely important, as well as figuring out how to make other iterations of them for figuring out other variables. And these three equations down here are just the kind of building blocks that should also be memorized. But yeah, this is G. So this is just an introduction to motion in under gravity. So free fall motion. So yeah, that's basically it.